Hi, welcome back to the channel. In this video, I'm going to discuss one of the Cambridge IGCSE past paper, which is Physics Paper 6, Alternative to Practical, October-November 2023, Paper 63. Are you ready to rock this paper? Let us get started. Now, let us look at the first question. Sand is a granular material composed of a very small, irregularly shaped mineral particles. A student determines the density of the sand by two methods. She uses the apparatus shown in Fig 1.1 and Fig 1.2. Method 1. A part 1. The student measures the mass of a 250 cm3 measuring cylinder as shown in Fig 1.1. So the question has already stated this is actually the mass of the measuring cylinder. Mass of measuring cylinder alone. Now, she pours sand into the measuring cylinder and measures the mass of the measuring cylinder together with the sand as shown in Fig 1.2. Use the values shown in Fig 1.1 and Fig 1.2 to calculate the mass M of the sand. I want the mass N of the sand alone. So if you want the mass of the sand alone, you have to deduct the mass of the measuring cylinder. So 219 gram is the mass of the measuring cylinder plus the mass of the sand minus the mass of the measuring cylinder alone. Then you get the mass of the sand, which is 143 gram. So 143 gram is the mass of the sand. Second part, the student measures the volume V1 of the sand in the measuring cylinder. V1 is equal to 108 cm3. Calculate a value for the density, rho 1, of the sand sample. Use the values from A part 1 and the equation rho 1 is equal to M over V1. Include the unit. Remember, you have to include the unit. So I'm going to just write it here. M is 143 gram. V1 is 108 cm3. So I use my calculator. I got 1.32 and the unit, this is gram per cm3. Now, before I write down my final answer, fill in the blank, I need to bear in mind that rho, which is the density of the sand sample, is actually being called calculated data. So I also want you to bear in mind that for calculated data, you have to look at the significant figures of the raw data. Raw data is the data that is being measured by measuring instrument. Row 1 is the calculated data because I'm using my calculator to do my calculation without looking at the scale or looking at the reading from any of the measuring instrument. So calculated data, look at the significant figures of your raw data. So look at the significant figures of M. The value of M is 143, which is 3 significant figures. Volume 1, 108. It is also 3 significant figures. Therefore, I will give row 1 3 significant figures as well. So 1.32, which is 3 significant figures for row 1. Method 2. B part 1. The student pours 100 cm3 of water into the measuring cylinder containing the sample of sand. Some of the water soaks into the sand sample and she waits for the water level to become constant first. That is good. Record the reading V2 of the water level in the measuring cylinder shown in Fig 1.3. Now, they make it larger for us. Could you see that? This is a curved line over here. It is a curve, then it is horizontal line. That is what we call meniscus. Whenever you take reading from the measuring cylinder, it is not possible for the water to form a straight line. The surface of the water to be straight line in the measuring cylinder due to its viscosity, right? So that is why we call this as meniscus whenever you take the reading, you bear in mind, reading must be taken below that curve, below the meniscus. So this is the reading that you are supposed to take. This is 150, this is 152, and this is 154. So my value of V2 is 154, 154 cm cube. Second part, calculate another value of for the density rho 2 of the sand sample. Use the values from A part 1 and B1 in the equation. Rho 2 is equal to mass m over V2 minus K, where K is 100 cm cube. Now, just do whatever they say. M is the one that you have determined earlier, which is 143 gram. So I'm going to put that 143 gram divided by V2 is the one that I just taken, 154 minus 100 cm cube. Use your calculator to do the calculation. The value that you should get is 2.65 gram per cm cube. So 2.65 gram per cm cube. That's the answer. Now the third part, on Fig 1.4, draw an arrow showing the correct line of sight for reading of volume of water in the measuring cylinder. Like what I say, due to the viscosity of the water and the glass of the measuring cylinder, it is not possible to form because some of the water will stick to the glass. That is why you have this curved line there. We call it as meniscus. Whenever you take the reading, you have to lower your eye position to a scale which is below the meniscus, which is here, below the meniscus. So your eye must be here. So you just draw an arrow here. That will do. Now see, another student wants to determine the density of the particles in a similar sample of sand. First part, explain why method 1 would not be suitable method for him to use. Now, let us scroll up to look at method number 1. Right, I don't have a problem with the mass of the sand, right? Because we use the top pen balance to measure the mass of the sand, so it shouldn't be any problem. But here, hey, I want you to see this. Look at the sand. When the sand is being filled, when the measuring cylinder is filled with sand, you don't have a flat surface filled by the sand. So there is a different levels of the sand, right? Due to the particles of the sand that come in different shapes, okay, different sizes, right? That is why you don't have, you cannot form a horizontal line on the measuring cylinder, which makes the reading of the volume, right, that will be taken from the measuring cylinder will be very hard. So the reading that you take might be larger. You see, some of the students would take these as the reading. Some of the students would take this peak as the reading of the volume. That will be very, very inaccurate. So how are we going to write that in Word? So I'm going to say that it is due to the gaps, right? Because the sands, they come with the sand particles, they come with different shapes, different sizes. So there must be gaps between the sand particles as well, right? So I would say that due to, okay, because this is 1 mark, I would just explain due to the gaps between the sand grains, volume taken might be larger than the actual volume of the sand. Volume taken might be larger than actual volume of sand. See part 2. Explain why method 2 would give a more accurate value for the density of the particles in this sample of sand. Method 2 is another method. Sand sample has already been filled into the measuring cylinder, and then you pour the water into the measuring cylinder. That is method 2. Why method 2 would give more accurate value? Because I said that the gaps between the sand grains are being filled with water, being filled with water. D. Describe two possible sources of inaccuracy in the measurements taken in either method 1 or method 2, even if they are carried out very, very carefully. So you don't talk about parallax error, you don't talk about not repeating the readings, etc. Because they have mentioned that these two experiments are being carried out very, very carefully with care. So I would say that volume 2 that is being calculated might be including the volume of the water. It's not the actual volume of the sand, right? So I would say that volume calculated in method 2 includes is equal. So I just put equal here so that it's easier for you to see. Is equal to volume of sand plus, okay, maybe a little bit of water, volume of water, right? Second possible sources of inaccuracy is might be using the measuring cylinder of a larger scale. Right, the measuring cylinder used is 250 cm cube, right? Could you see here? They have already told you, right? The student measures the mass of the 250 cm cube of the measuring cylinder. So the scale on the 250 cm cube of the measuring cylinder might be a little bit large, right? So I would say that the scale of measuring cylinder might be large. Or you could also say that due to the sand particles have no fixed shapes, right? It is very hard to make the surface of the sand to be flat. Surface of the sand, okay, I'll just put different color here. This is another sources of inaccuracy, right? So I will say that, okay, surface of sand is not flat or not horizontal, not flat, F-L-A-T, due to sand particles have no fixed, have different shapes, okay, different shapes and sizes, okay? So you might want to write this down as well. So if you have any idea or any possible sources of inaccuracy in the measurement that you want me to discuss, you want me to see whether it is correct, please do comment below. Now, second question, a student investigates the cooling of hot water in surroundings with different temperatures. He uses the apparatus shown in Fig 2.1. A, the student pours 100 cm cube of cold water into beaker B first and places the thermometer in the water. Measure and record the appropriate column heading of table 2.1, the temperature theta 1 of the water as shown in Fig 2.2. So let me see, this is 15 right here, I know, because this is 11, 12, 13, 14, 15, 16, 17, and this is 18 right here, 18. So I'm going to fill that in first. This is 18 degrees Celsius. And then theta 1, right? Is that theta 1? Yes, that is theta 1. And B, the student places beaker A inside beaker B. So beaker B is filled with water, and then beaker A is just placed inside beaker B as shown in Fig 2.3. So that water in beaker B rises between the sides of the two beakers. He removes the lid and pours 100 cm cube of hot water into beaker A. He replaces the lid and puts the thermometer into the hot water in beaker A. He records in table 2.1 the temperature, theta A, of the water every 30 seconds. Describe one precaution that can be taken to ensure that the temperature readings are as accurate as possible. First of all, if you want the temperature reading to be as accurate as possible, you need to insert in your thermometer and wait for the liquid in the thermometer or the mercury inside the thermometer has stopped rising before you take your pen and jot down the reading stated on the thermometer. Or the other precaution is that you have to make sure that the thermometer is inserted into the water because we are supposed to use the thermometer to measure the temperature of the water. So please, you have to make sure that the bulb of the thermometer is not touching the bottom of the beaker. So I will write down two precautions here. So if you prefer any one of these, feel free to use any one of these. So just one precaution is needed, but I will give you more than one so that you have more idea when you deal with different parts of your questions. So I will say that first one, wait till the liquid in thermometer stops rising before readings are taken. So another precaution is that, okay, you might want to say that make sure bulb of thermometer is not touching the bottom of beaker. This is very important as well. See, the student repeats the process for water at a higher temperature, theta 2, in beaker B. His readings are shown in table 2.1. Wow, okay. Write a conclusion stating in what way the temperature of the water surrounding beaker A affects the rate of cooling of hot water in beaker A. Justify your answer by reference to values from the reading. So justification, and they told you that reference to the values. So no choice, you have to put in values. I would say that temperature surrounding beaker A. Okay, one is 18 degrees Celsius, the other one is 48 degrees Celsius, right? So I would say that when, now let me find the rate of cooling, right? So let me find from T equal to 0 to T equal to 180. So what is the decrease in the temperature? So I just take 78.5 minus 62, and I got 16.5. So from t equal to 0 second to 180 second, the beaker A in cold water, which is 18 degrees Celsius, has already decreased by 16.5 degrees Celsius. But when the starting temperature is 48, beaker A is in warm water, the decrease in the temperature at t equal to 0 to t equal to 180 second is only 10 degrees Celsius. So I'm going to write that down. Here, I have to discuss about the rate of cooling. So I will say that when the surrounding temperature of beaker A is cooler, surrounding temperature is lower. Okay. Rate of cooling is higher because the temperature decreased by 16.5 degrees Celsius. So I'll say it's higher. So that is my statement. That is my conclusion. So I have to do some justification. So this is my justification. As temperature is 18 degrees Celsius, rate of cooling from t equal to 0 second to t equal to 180 second is 16.5 degrees Celsius per 180 seconds. So the rate of cooling is divided by 180 is 0.092, 0.0917, I write it right, degrees Celsius per second. And as the temperature is 48 degrees Celsius, rate of cooling from t equal to 0 second to t equal to 180 second, 180 second is 10 degrees Celsius divided by 180 second. Let me do it. 10 divided by 180, that gives us 0.0556 degrees Celsius per second. So that is the conclusion. Because when the temperature is lower, the rate of cooling is definitely higher, which is 0.0917. Now, D, calculate the average cooling rate R for beaker A cooling in cold water. Use the readings for beaker A from table 2.1, and the equation R is equal to theta A0 minus theta A180 divided by T, where T is equal to 180 second. Theta A0 and theta A180 are the temperatures in the water in beaker A at T equal to 0 and T equal to 180 second. Include the unit for the cooling rate. So R theta A, cold water at 0 is 78.5 degrees Celsius minus theta A, 180, which is 62 degrees Celsius. 62 degrees Celsius divided by 180 seconds. So the rate of cooling is equal to 0.0917 degrees Celsius per second. So I have to put it in terms of three significant figures because I have three significant figures for 78.5, that is three significant figures. 62, that is two significant figures. And 180, that's three significant figures. So if you see this kind of situation occur, because 62 is two significant figures. You have two significant figures for your raw data, and you also have three significant figures for your raw data. So how many significant figures you should give for your final answer? Now, let me make this easier for you. If you encounter with this kind of situation, you have different number of significant figures here, make sure that final reading before you fill in the blank, you can choose whether you want to put it in terms of two significant figures, which is equal to 0.092 degrees Celsius per second, or you want to put it in terms of three significant figures, which is 0.0917 degrees Celsius per second. So most of the time, we follow the least significant figures. So I am going to put it in terms of 0.092 degrees Celsius per second. Another student repeats this experiment at the same room temperature. State two other variables that she controls in order to obtain readings as close as possible to the readings in table 2.1. I said that the volume of the water must be made sure to be the same. So you have to control that. And you need to make sure that same starting temperature. That's it. After 180 seconds, the student measures the temperature of the water surrounding beaker A in the first experiment and finds that theta 1 to be equal to 49 degrees Celsius. First part, state the reason why this can affect the result of the investigation and suggest what effect it has on the value of cooling rate R. I said that because theta 1, you're supposed to get 48 degrees Celsius, but instead you get 49 degrees Celsius, right? So the reason is because the theta 1 itself is not constant. So how could it affect R? So the R would have to decrease because the starting temperature is not constant, right? So you see, this is the theta 1, right? When you calculate, where is it? The theta 1. So this is 48. Instead of 48, you get 49. So your theta is 49, so it will affect the rate of cooling. Now, second part, suggest one change to the experiment to reduce the effect in F part 1. So I say maybe because the volume of the water is too small, because when you put in beaker A, right? So due to the small volume of the water, the heat could be lost to the surrounding very quickly. So I say that use a bigger container with larger volume of water surround to surround A, right? To surround beaker A. That's it. Now, question number 3. A student determines the focal length of a converging lens. She uses the apparatus shown in Fig 3.1. A, the student sets the distance U between the illuminated object and the lens to 20 cm. She moves the screen until a sharp image of the illuminated object is seen on the screen. She then measures and records in table 3.1 the distance V between the lens and the screen. Describe a technique to obtain an image on the screen that is as sharp as possible in this experiment. Include in your description. Wow, they want you to include where the screen should be placed initially and how an accurate position for the sharp image is obtained. So how are we going to write that? So I have a lot of idea here. So I'll pour out my idea here. So which worth more than 2 marks here. I say that, okay, screen must be placed inlined with lens and illuminated object. And then screen moves forward and backward until a sharp image is obtained. Okay, you definitely don't know for sure that that is the sharpest image or not, but you see that, hey, I think this is a sharp image. So what do you do next? Okay, this is the next very important thing that you should do once you determine, hey, that's the sharpest image. Okay, once you are sure that that's the sharpest image, then move screen a little forward and a little backward to confirm the sharpest image. That is what you're supposed to do. Very important. Now, B, the student repeats the procedure for U equals to 30 cm, 40 cm, 50 cm, and 60 cm. Her readings are shown in table 3.1. For distance U equal to 20 cm, calculate and record in table 3.1 the value of U over V. Okay, this is U over V right here. U is 20 cm, V is 60 cm. Right, so 20 cm divided by U over V, 60 cm, and I got 0.333. I put it in terms of 3 significant figures because U over V is calculated data. U has 3 significant figures. V has 3 significant figures. That is why U over V is recorded as 3 significant figures as well. Now see, plot a graph of U, y-axis against U over V on the x-axis. Start your graph at origin 0, 0. Draw the best fit line. So this is my graph. So my scale on the x-axis, let me draw it out. My scale on the x-axis is, okay, one big box is 0.5. So this is my scale on the x-axis. And then this is my scale. X-axis, make sure that it is U over V. There's no unit for U over V, so you don't have to worry to put in the unit for U over V. But on the y-axis, right, because this is U, definitely there is a unit for U, which is in cm. So make sure that you put it in terms of cm. So I'm going to keep the ruler first. So this is cm, U slash cm, and then U over V. Right, this is my graph. And D part 1, determine the value of U naught when U over V is equal to 0. So you just look at the graph. Here, when U over V is 0, what is the value here? I got 13. So 13 cm is my answer, 13.0 cm. Right, so the range given, thank goodness, mine is on the smallest range, 13 cm to 18 cm. The second part, the gradient of the graph is numerically equal to the focal length, f of the lens. Determine the value of f for this experiment. Show clearly on the graph how you obtain the necessary information to determine the gradient. So you know that gradient is equal to f. So the gradient, okay, or f is equal to gradient. I put here, f is equal to gradient. So you have to know gradient is from math. You need to have two coordinates, y2 minus y1 over x2 minus x1. So you have to show how you obtain necessary information. That means you have to show your x2, your x1, y1, and your x2, y2. So this is my x1, y1, and the other one is my x2, y2. So I use quite big triangle right here, so you can see. So these are all the coordinates that I need, right? So now I'm going to determine the value of f. Now my y2 64, my y1 is 13. 64 minus 13 divided by x2 is 3.25, x1 is 0, 3.25 minus 0. So 64 minus 13 divided by 3.25, and I got 15.7. So 15.7 cm is my answer, 15.7 cm. So how do I get cm? Because y-axis is in cm, x-axis has no unit. So this is in cm, this one has no unit. I put it in terms of 3 significant figures, or you can put it in terms of 2 significant figures, because 64 and 13 are 2 significant figures. 3.25, but 64 here, you could see that, okay, yeah, but 64 here is actually calculated from here, U 60.0, that is 3 significant figures. So it is up to you to put it in terms of 2 significant figures or 3 significant figures. It doesn't matter. So E suggests one precaution that can be taken to ensure measurements are accurate in this experiment. So when you scroll up again, if you are blank, you don't know what to write, scroll up to the diagram. Hey, this is related to illuminated object. There is only one fixed answer, which you could say that conduct the experiment. Okay, in a dark room so that the sharpest image is confirmed very sharp. Right. Now, number 4, last question. A student investigate the brightness of the lamp again. Plan an experiment to investigate how the intensity means the brightness of the light, produced by the lamp is affected by the current in the lamp. The apparatus available includes a lamp and a power supply, a light meter, which measures the intensity of light arriving at it, and a meter, a variable resistor. In your plan, you should first complete the circuit diagram in Fig 4.1 to show the variable resistor connected to control the current in the lamp. Variable resistor, or the other name for it is called rheostat, right? So if you want to control, right, this variable resistor must be connected here in series. So I just draw this length, and this is a symbol of variable resistor. And I put this as a variable resistor. That's it. And I'm done with the first one. State the key variables to be kept constant. Okay, I will write here as controlled variable. Controlled variables. I maybe want to write that the voltage of the power supply. So when you turn to 1 voltage, you use that one until the end of the experiment. So I say voltage of power supply, and make sure that the temperature of the lamp, must be constant, because if the temperature of the lamp is not constant, when the temperature of the lamp increases, it will also increase the resistance of the lamp, which decreasing the current, right? Therefore, the lamp will be less bright. And I also want to say maybe the distance between the light meter and lamp, make sure that it is the same all the time. So you can see here, this is the light meter and the lamp. Make sure that this distance is always constant until the end of your experiment. So that is done. And explain briefly how to do the experiment. That is your method. So I'm going to write here methods. So I will say that, okay, the first method, set up apparatus as shown in diagram. And second, power supply, because I want to make sure that the voltage of power supply is constant. So I suggest power supply is switch on to 3 volt. Remember, for a lamp, right? You don't use a very large voltage because you could burn that lamp, right? We use a small voltage. And okay, after that, I use light meter reading. Light meter, okay, I don't want to use the light meter, and ammeter. Ammeter readings are taken. Then after that, okay, don't just take the reading. What is the function of variable resistor? So you have to repeat the experiment. Repeat the experiment by adjusting variable resistor for different current readings on ammeter. So the last part of the method is always repeat the experiment. So I'm done with that. And then after that, you have to draw a table with column headings to show how to display the readings. You are not required to enter any readings in the table. So I will just say, this is my table. So my table, I will put ammeter reading, which is ampere. And then the other one is the intensity, yeah, of light, which the unit is watt per meter square. So I'm just going to put in the unit here. Here, this is my table. And then the last part, explain how to use the readings to reach a conclusion. So conclusion, I would say, very easy, because I have 2 variables here. I will just say plot a graph of ammeter reading, or the current, against intensity of light to see the relationship, because I don't know the relationship. I need to plot the graph. I need to conduct the experiment, because we are just a planner, right? So that is all about October-November 2023, paper 63. But if you have any comment, any idea you want to add into the discussion, please feel free to comment below. I welcome your comment. So thank you very much for watching. So I hope you find benefits in this video, and hope to see you again in the next video. Bye.